Something strange is happening on Jupiter, and NASA can't explain it. Instruments started picking up unusual signals deep within the planet's atmosphere, signals that seemed to change every few hours. Then, as the mysterious object known as 3I Atlas moved closer to Jupiter's orbit, those readings intensified in ways scientists had never seen before. Some experts believe it could be interacting with Jupiter's powerful magnetic field, while others think it's triggering something hidden beneath the planet's clouds. Keep watching, because this video is going to reveal what NASA really saw on Jupiter as 3I Atlas approached.
We are learning that Juno has found an FM signal emanating from one of the gas giant's moons. However, this is the first time the phenomenon has been seen emanating from the moon.
Three I Atlas is not an ordinary comet. It's an interstellar visitor, a traveler from beyond our solar system. Detected in mid-2025 by the Atlas telescope in Chile, it became the third confirmed interstellar object after Oumuamua and 2Borisov. What makes 3I Atlas different is its incredible speed and path. It isn't bound by the sun's gravity, which means it will pass through our solar system once and never return. Scientists estimate its size to be somewhere between 300 meters and 5 kilometers wide. As it moves closer to the sun, the comet's frozen surface heats up, releasing gases and forming a bright coma and a long tail that stretch across space. Observations suggest that 3I Atlas is rich in carbon dioxide and carbon monoxide, materials that hint it formed in an extremely cold region far outside any known planetary system. Its trajectory brings it near the orbit of Jupiter, giving astronomers a unique opportunity. Jupiter's immense magnetic field and gravity could interact with the comet's plasma tail, creating disturbances that can be detected by NASA's Juno spacecraft. Any such interaction might explain the strange signals scientists have recently observed coming from Jupiter's magnetosphere. Now, let's uncover what's going on Jupiter. Every time we think we figured out this gas giant, it surprises us again. With its unpredictable nature, violent storms with winds reaching up to 640 kilometers per hour, 400 miles per hour, and the mysterious metallic oceans thought to exist deep within its core, Jupiter remains a puzzle that continues to challenge researchers. Decades of research have revealed just how complex Jupiter truly is. Recently, astronomers discovered 12 additional moons orbiting the planet, bringing the total count to 92, the most of any planet in our solar system. These newly found moons range in size from about 1 to 3.2 kilometers. Most of these moons follow long, distant orbits, with 9 of the 12 taking more than 550 days to circle Jupiter once. Scientists believe that many of these outer moons move in the opposite direction of Jupiter's rotation because they were once asteroids captured by the planet's gravity. For years, many believed that Jupiter acts as a cosmic shield, protecting Earth from dangerous objects in space. Some astronomers even suggested that life on our planet might not have developed without Jupiter's protection. But new evidence is raising questions about whether the gas giant truly serves as Earth's guardian. Long-period comets, which come from the distant edges of the solar system and take thousands of years to orbit the sun, often enter the inner regions. Because of Jupiter's strong gravitational pull, most of these fast-moving icy bodies are flung out of the solar system before they get anywhere near Earth. This means collisions with long-period comets are incredibly rare, happening only once every few million or even tens of millions of years. In these cases, Jupiter really does act as a shield, keeping our planet safe. However, Jupiter's gravity isn't always helpful. It has both protective and harmful effects on life on Earth. On one hand, Its immense gravity prevents nearby space debris from merging into a planet, which led to the creation of the asteroid belt, a vast region of rocky fragments between Mars and Jupiter. On the other hand, Jupiter's gravitational force can alter the paths of asteroids, sometimes sending them toward the inner solar system and closer to the Sun. This can increase the chances of impacts with Earth, something history has already shown us. In 1770, Lexell's comet came within just about 1,000,000 miles of Earth, an extremely close pass in cosmic terms. Scientists believe this comet originally came from the outer solar system, but was redirected toward Earth after a close encounter with Jupiter. After completing 2 orbits around the Sun, the comet again approached Jupiter 9 years later, which then flung it completely out of the solar system. The idea of Jupiter being Earth's shield was supported by earlier computer simulations. These studies showed that the gas giant could eject countless long-period comets from the solar system. The famous 1994 impact of Comet Shoemaker-Levy 9 into Jupiter was also seen as proof of this theory. But back then, computing power was limited, and researchers had to make many assumptions and simplifications. Today, we have access to far more accurate data. Scientists now observe many more short-period comets and near-Earth asteroids crossing Earth's path compared to long-period ones. With advanced simulations, a new picture has started to form. Jupiter's strong gravity interacts with the asteroid belt, creating gravitational resonances that push unstable asteroids out of their orbits and sometimes direct them toward the inner solar system. Collisions between asteroids can also break them apart, sending smaller fragments into these resonant zones. The inner edge of the asteroid belt is especially affected by something called secular resonance, which drives material inward toward the planets. Jupiter's massive size allows it to both protect and endanger Earth. It can fling comets and asteroids out of the solar system entirely, as it did with Lexell's comet, but it can also pull some of them into orbits that cross our own. If Jupiter were only 1/5 of its current mass, it would still disrupt comets' paths, but wouldn't be powerful enough to remove most of them from the solar system, resulting in a much higher number of impacts on Earth. The frequency of cosmic impacts plays a major role in shaping the long-term evolution of life on any planet. Earth's geological history shows that one major collision, roughly every 100 million years, allows enough recovery time for the biosphere to rebuild and flourish. But if such impacts occurred every few million years, the damage could be catastrophic, constantly wiping out ecosystems and preventing the formation of stable life. Some scientists suggest that collisions with Earth may have been how water first arrived here. But what about Jupiter? How did water get there? Water vapor on Jupiter was first detected in 1995. This discovery came from NASA's Galileo spacecraft, which conducted detailed observations and measurements of the planet and its moons. Using instruments like the near-infrared mapping spectrometer, Galileo identified the presence of water vapor in Jupiter's atmosphere during one of its close flybys. Recent data now shows that water makes up about 0.25% of Jupiter's atmosphere above its equator. While that may sound small, it actually represents an enormous quantity of water. Jupiter, likely the first planet to form in our solar system, holds large amounts of gas and dust left over from the Sun's formation. Understanding how much water is contained within Jupiter helps scientists better understand how our solar system itself was formed. In recent years, researchers have used telescope data to confirm significant amounts of water within Jupiter's Great Red Spot. Since its launch in 2012, NASA's Juno spacecraft has been orbiting the gas giant, capturing close-up images of its swirling clouds. Equipped with advanced instruments, Juno has provided even stronger evidence that Jupiter contains large quantities of water. Because Jupiter's mass is more than twice that of all the other planets combined, even a small fraction of water makes up an enormous total amount, far greater than all the water found on Earth. The water in Jupiter's atmosphere is also responsible for its dazzling lightning displays, which are 100 times brighter than lightning on Earth. It even causes the formation of strange, hail-like particles. Lightning has been observed in Jupiter's water clouds, where droplets of water collide with electrically charged ice crystals. However, Juno has also detected dimmer flashes of lightning at higher altitudes in Jupiter's atmosphere, where temperatures plunge to around -87 degrees Celsius, too cold for liquid water to exist. So, how does lightning occur under such freezing conditions? The answer lies in ammonia, a compound that acts as a natural antifreeze in Jupiter's atmosphere. In the upper atmosphere, water ice crystals mix with ammonia vapors and melt, forming ammonia water droplets. These droplets collide with ice crystals from below, generating electrical charges that create lightning. Deeper in the atmosphere, the ammonia water droplets continue to grow larger until they become too heavy to stay suspended. At that point, they turn into massive hailstones similar to those found on Earth. Scientists believe these mushball-like hailstones fall deep into Jupiter's lower atmosphere. Now, let's travel even deeper into Jupiter's interior. For decades, scientists believed that all giant planets in our solar system had solid, rocky cores. That idea was widely accepted, until new data began to challenge it. By studying Juno's orbital data, researchers are learning how matter is distributed inside Jupiter. These studies have revealed a surprising mystery hiding at the planet's core. Jupiter's inner regions experience pressures far greater than anything on Earth, along with temperatures soaring up to 20,000 degrees Celsius. To simulate these conditions, scientists use high-powered lasers to compress materials and reproduce Jupiter-like pressures in laboratories. At the University of Rochester's Center for Matter at Atomic Pressures, researchers are leading efforts to uncover how materials behave under such extreme conditions. The density of matter in Jupiter's core depends on its composition and physical structure. Recent findings show that Jupiter's core isn't as compact as once thought. Deep within the planet, only about 18% of the material is rocky. The rest of Jupiter is made up mostly of hydrogen, around 90%, with about 10% helium and tiny traces of other elements. In the planet's outer layers, hydrogen exists as a colorless, transparent gas, much like it does on Earth. But as you move deeper into Jupiter, the immense atmospheric pressure compresses hydrogen into a dense, fluid form that behaves like a metal. So, what exactly is this strange substance? About 10% of the way toward Jupiter's center, the vast hydrogen gas envelope is squeezed so tightly that it transforms into something unique: liquid metallic hydrogen, a state found nowhere else in our solar system. Liquid metallic hydrogen has properties that resemble water. It has low viscosity, excellent electrical conductivity, and transfers heat very efficiently. Inside Jupiter, this substance is found in huge amounts, turning the planet into a massive generator. On Earth, elements can exist as solids, liquids, or gases, depending on temperature and pressure. Hydrogen on our planet is usually a gas, but it can be compressed and cooled to become a liquid or even a solid. However, even in those states, hydrogen stays nonmetallic and remains a poor conductor of heat and electricity. Metals, on the other hand, are good conductors because of how their atoms are arranged. Deep inside the gas giants of our solar system, hydrogen is exposed to extreme temperature and pressure. These extreme conditions allow hydrogen to take on unusual forms, including liquid metallic hydrogen. Under such pressure, hydrogen atoms lose their electrons, creating a mixture of free hydrogen nuclei and free electrons. This high level of electron movement gives the material metallic properties. Some scientists believe Jupiter's core might contain vast oceans of liquid metallic hydrogen. Based on earlier calculations, the mass of Jupiter's core could be 12 to 45 times that of Earth. A 40,000-kilometer, 25,000-mile layer of liquid metallic hydrogen, combined with Jupiter's rapid 10-hour rotation, generates a massive magnetic field stretching an incredible 725 million kilometers, 450 million miles, across space. This is the largest magnetic field in our solar system, and it carries mysteries of its own. When scientists studied regions more than 320 kilometers below Jupiter's atmosphere, they discovered a new area called the Great Blue Spot, not to be confused with the planet's famous Great Red Spot Storm. Researchers knew Jupiter's magnetic field was complex, but they didn't realize just how unusual it really was, and the Great Blue Spot turned out to be a major clue. Jupiter's magnetic field is about 20,000 times stronger than Earth's. But now, scientists have found that its strength constantly changes. Unlike Earth's dipole magnetic field, Jupiter's magnetic field originates from a large area in its northern hemisphere and re-enters near the South Pole. Researchers also found a concentrated region just south of the equator, known as the Great Blue Spot. In a sense, this area acts like a second South Pole near Jupiter's equator. The massive storm that has lasted for centuries is likely caused by large amounts of ammonia in the atmosphere. The strength of the magnetic fields within the Great Blue Spot fluctuates by up to 1% each year, alternating between stronger and weaker regions. By the end of NASA's extended Juno mission in 2025, scientists expect to have enough data to test their theories. As studies continue, more mysteries about Jupiter are being uncovered. Since the Great Blue Spot and the Great Red Spot are located at the same latitude, researchers believe there may be some connection between the two. Gas giants are known for their high temperatures, especially in their upper atmospheres. In our solar system, there are two such giants, Saturn and Jupiter. However, Jupiter's temperature is not uniform throughout its structure. The largest planet in our solar system is most famous for its enormous storm, the Great Red Spot, which is twice the size of Earth. But Jupiter also has other spots. One of them, called the Great Cold Spot, is nearly as large and has been observed for many years. At its biggest, the Great Cold Spot measures about 12,000 by 24,000 kilometers. Unlike the red spot, it is a region where temperatures drop sharply, around 200 degrees Celsius cooler than the surrounding atmosphere. The Great Cold Spot is unstable, disappearing and then reappearing over time. Scientists have found that this recurring phenomenon is triggered by Jupiter's auroras. Because of this link, the Great Cold Spot is believed to be as old as the planet's polar lights, thousands of years old. Like Earth's, Jupiter's auroras are created when charged particles interact with its atmosphere near the poles. But the gas giant's auroras are far stronger and more stable because they receive particles from both the Sun and its moons. Recent findings show that these auroras transfer energy to Jupiter's atmosphere, creating a temperature difference between upper and lower layers. This difference forms swirling vortices, producing a cooler patch distinct from the aurora itself and its surroundings. Earth experiences similar effects, but on a smaller and less consistent scale. Jupiter's fast rotation, which traps heat in certain regions, and the variability of these energy transfers make its auroras far more intense and persistent. Another fascinating discovery about Jupiter is that it doesn't actually orbit the Sun in the way most people think. The center of gravity between Jupiter and the Sun isn't inside the Sun. It lies just above the Sun's surface. In space, when a smaller object orbits a larger one, both actually move around a shared center of gravity. Take Earth and the Sun, for example. The center of gravity between them lies so close to the Sun's center that it's almost unnoticeable. As a result, the Sun appears stationary, while Earth seems to orbit around it perfectly. The same thing happens with the International Space Station and Earth. Both orbit a shared center of gravity, But because Earth is so much larger, it appears still while the ISS circles around it. This principle applies to most planets in our solar system. Even Saturn doesn't shift the Sun's position significantly. However, when the difference in mass between two bodies is smaller, the effect becomes noticeable. In Jupiter's case, its immense mass pulls the center of gravity, called the barycenter, to a point about 1.07 solar radii from the Sun's center, or roughly 7% of a solar radius above the Sun's surface. This means both the Sun and Jupiter orbit around that shared point in space. As exploration continues, the depths of Jupiter will likely reveal even more surprises. Stay tuned to discover what comes next from the largest planet in our solar system. And thanks for watching.